some inverse problems in biomedical imaging. So.
Yes, thank you very much for the invitation. I was here 10 years ago in 2007 for a conference also in IMPA for celebrating the Alberto Calderón paper on the AIT problem. And at that time, I was working a lot on geophysics, on air pollution, data simulation, and lithospheric plates, etc., seismic in geophysics, etc. So I was this year too there. I am also I participate in Chile in a Center of Climate Change and Resilience. So it's my other part. But some years ago, I moved a little bit to biomedical imaging with a colleague of another university, also with the help of Gunther Ullmann, who is Chilean, and he was investing a lot to come to Chile, and we were organizing a lot of conferences. And so I will present what we're doing at the Center of Mathematical Modeling in Chile related to these biomedical imaging inverse problems. So just for the young people, this is a very, very fruitful ground to develop inverse problems, of course. In particular, in imaging, there's a lot of techniques now, and there are new techniques appearing each day to help the medical diagnosis. And so most of these methods are based on the propagation of waves or the diffusion of light into the body, since it's a lot of water. We have a lot of water there, so it's essentially the propagation into water of this radiation, light, elastic waves, electricity, etc. So I will talk about four different problems, but I just give detail in the first one, but it's just to have some context. Okay, so the main topic will be about nuclear medicine, an application where we are working on, and is related to the radiate transfer equation also. And then I will just mention 3 other applications we are developing at the Center of Mathematical Modeling. One is related to magnetic resonance, and some applications in medicine. Then we have also some applications about porous media. We're interested in lungs, in bones, and also in elastography. This is more theoretical. We are interested in applying some stability and uniqueness techniques in the case of viscoelastic media. Okay, so I think these are different, more applied or more theoretical lines of research. Okay, my former formation was I am a mathematical engineer, and then I am a mathematician also. So in nuclear medicine, the technique we are studying is called SPECT. It's very well known in nuclear medicine. I will explain for people what is exactly SPECT. And with this, exactly this inverse problem. This inverse problem is called the identification problem in SPECT, and it's the simultaneous reconstruction of a source of gamma rays and the attenuation of the media. So, but going to the beginning, also for the young people, for the students who can be motivated for this kind of problems, inverse problems, everything started with X-rays and with the scanner, and in order to understand the images I will show later, say that the idea is to combine or to move, to combine X-rays in different angles and try to have some three-dimensional reconstruction of the attenuation. So in order to understand attenuation, essentially, when you have an X-ray, which is an electromagnetic wave, crossing, okay, and this is a figure of Samouly-Siltanen, courtesy of Samouly. You have the intensity of this ray decreasing when you cross the different organs, the different materials, the different media, and then you register this decrease, this ratio of decrease, and you have an image. Okay, this is the first essential ingredient, and this is called attenuation. Attenuation of the media, typically A of X in our presentation. And then you can move. Also, this is a video made by Samouly, and you can combine. You can have different X-rays, and then you turn around the body, and you find the different shadows of these rays, and this is called a sinogram. This sinogram is the measurements. These are the measurements you have, and the main idea is to recover, okay, the image from this sinogram. And the main tool is the inverse radon transform, and we have 100 years before this achievement in 1907, okay? So we will use this tool. And also, in the case of nuclear medicine, they use not X-rays, but they use gamma rays, which are really energetic electromagnetic waves, the most energetic ones, and discovered, okay, a long time ago. And this type of gamma rays are used to really detect some very specific signals. In this case, the main applications are in neuromedicine, to study some, for instance, Alzheimer, epilepsy, or for cancer treatment. These are the typical machines you use in nuclear medicine. One is a SPECT machine with 2 gamma ray cameras turning around the patient, and the other one is the PET scanner with several cameras, okay, around the patient. The main difference we will see, one is cheaper than the other one. One can take more time. PET is longer. Okay, there's some difference, but essentially they use this gamma ray source of gamma rays inside the body, and I will explain mathematically. This is a scheme of how it works. You have this. This is the case of SPECT, and this is a case of PET. The main idea is that you have some gamma ray source or some photon coming from inside the body and going to some detector. This detector can be collimated or not. Collimated means that it receives the signal in just the parallel, the transversal or parallel direction here, and here it's not collimated. You can receive photons in all the directions. Okay, so this is the first difference between PET and SPECT. And in the case of SPECT, the main signal are the so-called ballistic photons, which are gamma rays going directly to the camera. And in general, you neglect these scattered photons. Okay, you can receive the scattered photons, but in general you don't use them. And in the case of PET, you use also the fact that you have some annihilation in the nucleus of the atoms, and then you have two photons going in opposite directions, and you try to obtain the main location of the source by synchronizing the arrival time of these 2 photons. Okay, so they are completely different, but both are based on a mathematical tool called the attenuated radon transform. This is an example of application in the case of neuropsychiatria. Okay. The first image is the case of an Alzheimer case where you can see the idea is to detect from this gamma ray source, okay, regions of the brain where the blood perfusion, which is the blood diffusion of blood, which is a signal of brain activity, has decreased. So there's some regions where you have less blood, say. And it's the case also in epilepsy. You have, for instance, before an attack and during an attack, difference in perfusion of blood. So you can identify the regions of the brain that are involved, for instance, in this damage or this activity. And you can also have view planes, etc., etc. So it's very useful as technique in medicine. And as I said, the main tool, mathematical tool, is the so-called attenuated radon transform. So the attenuated radon transform is simply the integral of the source along lines. Okay, so you have the source, you have the integral along lines, and you receive here the detector, which is collimated. So in this direction, you receive the integral of f along this line. But the integral is weighted, but some exponential weight, which is related to the attenuation that we present for X-rays before. So essentially, this attenuation is related to also along the line. So this is the attenuated radon transfer, which is denoted with R for radon, of course, with a sub-index A to say that it depends on the attenuation. Okay, so this function depends on F and depends on A. Depends linearly on F, but depends non-linearly on A. And this is the main difficulty to recover both parameters, F and A. So this is exactly the inverse problem for SPECT, is to recover the source from these quantities, okay, along lines. So you have this in general, physicians in practice, you assume that the attenuation is known. You have two choices. One choice is to say, okay, attenuation is just attenuation of water, or is constant, okay, some attenuation constant, or you can have an information of the attenuation by another medical technique. For instance, you can do a computed tomography, a CT, so you have the attenuation of X-rays, and then you can pass the attenuation of X-rays to attenuation of gamma rays by some transformation, and you have an idea of the attenuation of the media by another, okay, technique. So you can see in hospitals nowadays some SPECT CT machines which mixed gamma rays and X-rays to have both simultaneously. Okay, but the idea is to mathematically try to do that without another technique, with the same data. Important in notation here, theta is the angle of the line, theta orthogonal is the orthogonal of the line, and S is the position of the line with respect to the origin. Okay, so this is a function of two variables, the position of the line and the direction, or you can consider it as a function of the position and the angle. Okay, but a two-dimensional function. And there's, in the case in this simplest case, there's an inversion formula for the attenuation radon transform, which is a little bit more complicated than the original inversion of radon for the non-attenuated radon transform with A equal to 0, say. And it involves several calculations. You can do it numerically. There's some ways to do that with a good controlled approximation error. You can do that. So this is one possible way, but you need to know the attenuation. The attenuation is something you need to know here in the formula to recover F. Okay. So the original idea was proposed by a colleague working on a hospital in Chile. He was saying we can see in the machine, we can register not only the high energy ballistic photons but also the low energy scattered photons. Since the scattered photons have lower energy, you can distinguish them from the ballistic ones by observing the energy. So this was the idea we tried to use. If we use this scattered information, maybe we can recover not only the source but also the attenuation. And this is a very long. This has attracted a lot of interest. This problem of recovering simultaneously F and A. So, for instance, numerically, there's a lot of people trying to recover both F and A from just the ballistic information. But in general, theoretically, there are no uniqueness. So there's some counterexamples showing that you can have two different pairs of source and attenuation with the same measurements, ballistic measurements. So in practice, what do you see? You see some superposition of this attenuation and source when you try to recover both. Okay, but you can also do a lot of things to try to separate them, etc. But it's a little bit artificial. So the idea here is to really correct that. And here this is a photo of the real machine on a SPECT screen, and you can see there's some typical energy, which is the energy of the in this case is technetium 99, is some radiative thing with this energy, and so this is the typical energy of the gamma rays that are going directly to the camera. And then this is the typical energy of the scattered photons, that have collided once or twice. So you can separate a little bit. You can separate both quantities. And then you have two measurements. You can consider this is the classical measurement for SPECT, which is the integral of the source attenuated. So it's the radon transform of F, attenuated radon transform of F, essentially. But you can also use you take the ballistic photons, you consider they are scattered once, and then you put these scattered photons as the new source for the second measurement. So the scattered photons are considered as a new source. You have the red source directly, and then you have the blue source, which is after one scattering. So mathematically, it means you have to integrate twice, the ballistic ones. This is a typical decomposition you can do with the first scattering, the second scattering, etc. And also you have to consider, in this case, in the case of SPECT, you are not considering this problem. You need to know this scattering kernel, and this is related to spherical particles or what is the type of scattering you have? Since if you put a scattering, you have another parameters to determine here. So you have another measurement, but you have more parameters to determine. So in order to avoid that, we will suppose some assumptions. For instance, the scattering, depends only in the cosinus of the angle of incidence between the particles, so the dot product of the angles. And in general, we also consider that this is almost uniform, so we consider that the probability to go after collide a photon, the probability to go in other direction is the same, but with a perturbation, with a small perturbation. And we consider now we have three parameters. We have the attenuation, the total attenuation, the source, and the scattering kernel. So this is a problem. We have two measurements, but three functions. So it's the same. So the solution, one solution should be to consider the second scattering, but the second scattering in practice, you cannot see here clearly the second scattering separated by the first scattering in the energy window. So you cannot do that. So our solution was to consider that, in fact, the attenuation and the scattering kernel are proportional, or one function of the other. In fact, this is related to, okay, to some assumptions. So you will consider that K and A are related. And it works with real data, so it's not a bad assumption. And this is related to this scattering assumption. This is the real, or for spherical particles, you have this Klein-Shina formula saying that the probability to go in the right direction is larger than the probability to go in the opposite direction. And also the energy, you have the energy here, a quantification of the quantity. If you go in the right direction, no collide, the energy is not decreasing, but if you go in the opposite direction, the energy is decreasing in some amount. So this is the main idea, but okay, we can go further with that. So we will consider that in fact the measurement depends on this scattering phi here. Okay, but this is a summary of the measurements written in a mathematical manner, simple mathematical manner. In this case, so the ballistic measurements is the radon transform attenuated, okay, of the source, and the scattered measurements are the radon transform attenuated of something which is a function of the attenuation. So now the inverse problem is to recover both the source and the attenuation from these two measurements. And this is a nonlinear inverse problem now. If you compute the inverse radon transform here, okay, you need to know the attenuation. Okay, so the idea is to do something iteratively or linearize this problem, etc. This is the main idea, but it's no more a linear problem as is the case of a standard spect. So the main idea in our analysis, this is the mathematical analysis, the main idea was to do something possible, linearize. Okay, it's non-linear, linearize, please. Don't panic. So the idea was to linearize, consider that there were some known attenuation and source reference, and then we made some perturbations of the attenuation delta A and of the source delta F, and we compute the derivative of this operator. The operator is the operator that takes both measurements, A0 and A1. So take the derivative of this operator with respect to F and with respect to A. And the derivative can be decomposed into two parts, one part which is clearly invertible and the other part that is clearly small. So the main idea is to decompose this operator, or this linearized operator, in one part which is invertible. And why this part is invertible? Since in general, if you have these two measurements, okay, you can take the second measurement, divide by this M1, obtain delta A, and with this attenuation delta A, you can compute the source delta F. So in general, you can easily, this is as a triangular, okay, operator, since the second component depends only on delta A, and the first component depends on delta A and delta F. So you can solve the second equation and then replace in the first and obtain delta F. Okay, this is so it's easily invertible, and the second one depends also on delta A and delta F, but depends also. Okay, it's complicated, but in general, the idea is that is small is if A is small. Okay, so this is the main idea, and okay, in general, when you compute this derivative, there's a problem, mathematically speaking, big problem, is that when you compute the derivative of the radon transform, the attenuated radon transform, you obtain some new transforms with new weights, which are no more attenuated radon transforms, are generalized transforms. So a generalized transform is, okay, you have now the integral of f attenuated but some weight, okay? But now it's not an exponential weight, it's another weight. In this case, for instance, the weight depends on a and f, okay? It's some function of a and the integral of f, etc. And in general, there's no a general theory about weighted radon transforms. You don't have inversion formulas in general, and the analysis is difficult. But there's a very useful result here saying that in general, this generalized transforms depends continuously on the data, provided that the weight is regular enough. In this case, the weight has to be in some Holder space with alpha, okay, bigger than k plus 1 or 2, etc. So you have the regularity. You can have some stability estimates, but you need to consider regular weights. This is the main problem. And the regular weights are related to regular attenuations and regular sources, etc. So you have to regularize a lot to have results. But in general, the main theorem is that, in fact, L, the first part of the linearized operator is invertible, okay? With this rule, you divide by m, and then you replace to obtain the source here. And is continuous, okay? And the other part of the linearized operator is small with respect to, okay, a. So invertible plus small, you can invert, okay, identity plus something which is bounded, you can invert it by Neumann series, for instance, you can prove something. So you can obtain, finally, I will not write the theorems now, since they became a little bit technical due to regularization, etc. But we have theoretical results for uniqueness and stability for the linear problem, linearized problem, and local uniqueness and stability for the nonlinear problem. Now, what about reconstruction? So reconstruction, you need numerical methods. We have implemented a lot of different methods. The first one based on theory is the Neumann series. Also some fixed point methods, but we don't have the theoretical conversions of these methods, some Newton methods, and some algebraic reconstructions. I will explain that. So you can obtain, this is from real data, you can obtain results. In this case, we were comparing the normal spec using just ballistic measurements with the spec with scattering measurements, and this is the recovery of the source. So the recovery of the source is very similar. You have no much improvement in the recovery of the source, but what you win is that you can obtain at the same time the attenuation of the media. Yeah? The main problem was that in this case we didn't know the real attenuation of the media in practice. We had these measurements, but we didn't know the real attenuation, so we had to construct a real phantom to evaluate the method. So I will show you, before that, in general, this inversion formula, this attenuated radon transform inversion formula is valid when you have isotropic scattering. If you don't have isotropic scattering, you need to develop another method which is called algebraic reconstruction, which is essentially to divide the image in pixels and then to compute the integrals, okay, by quadrature formula. You compute the integrals and you compute all the operators as a big matrix, and you try to invert this matrix by some numerical methods. It's expensive in time and in memory, but it's the only way to do. And here I have this is an academic example without real method, but simulated ones. So we have the ballistic These are the sinograms. You see, these are the sinograms we saw before. So this is ballistic sinograms, okay, and this is the scattered sinograms. So from these sinograms with noise or without noise, you try to recover the attenuation and the source. So in this case, for instance, this is the attenuation, the reconstructed attenuation. When you have noise, you have some problems. Here we don't apply any image processing, post-processing tool. So it's the direct result of the method, and this is the result for the source. This was using Newman series, okay? And this was using the algebraic reconstruction, the same example. So you can see the results are okay. You can do this is the work we publish in the Trends in Mathematical series. I acknowledge the possibility to publish that in this conference. And so in practice, we construct a real. This is my pencil. We construct here a real phantom. Okay, the idea was to have scatterers of different sizes, okay, and a source of a radiative source, and try to recover that. In particular, the attenuation, not the source. The source is easy, but the attenuation. And now we know the attenuation, and these are the results. This is the phantom. So at some moment you are just cutting the cylinder, and this is the computed result. At some level you are cutting the cylinder and one scatter, okay, and at some point you are cutting just the scatterers. And you can see the two big ones, but not the smaller one here, which is the pencil, in fact. So we have these non-yet published results, but the method is working with real data. This is important. And real error, of course. So the second application is really kindergarten mathematics, as Nashman said once. Was really simple from the mathematical point of view, but was really complicated to enter in this problem and to solve it, also with collaboration with people working in practice, in experiments. So the main idea is to enter into this world of magnetic resonance imaging, which is based on the line of water spins of hydrogen nuclei of water, and try to do something applied coming from mathematics, okay? So essentially the equations that are behind are the equations called the Bloch equations for magnetization. Magnetization is a vector field, okay, which satisfies some transport equation, where this velocity here can be, for instance, the velocity of blood, okay? You have the spin precession. We have some relaxation times related to the magnetization in different directions, x, y, and z. So the main idea is to apply first a very big, here is this B, a very big magnetic field in order to align all the spins, and then have a total magnetization, which is in general different from zero and satisfies this equation. Then this magnetization, you can write it, you can drive it to some plane. So the important components will be the x and y components, and then you can separate or you can distinguish the modulus and the phase of this magnetization, and then you can work just with the phase. That satisfies also transport equation, and try to recover, for instance, the velocity of the blood from the phase of the magnetization, finally. This is a second gradient, a second magnetic field you can apply in order to move, okay, to test this equation and recover this velocity. And this is called phase contrast magnetic resonance, okay? And it's used to recover velocities or displacements for elastography, okay? So velocity in this case is in what we were interested. So magnetic resonance is not only to recover one physical parameter, but also to recover velocity, okay, and displacement. It's very important. So what was our contribution was very simple. In fact, there were some non-uniqueness in the recovery of the velocity from phase contrast, since this phase was, in fact, known by a factor 2 pi, or some multiples of 2 pi. So in fact, what we did was simply to consider more measurements, okay, sum up these two measurements and have just one global minima and not a lot of local minima. It was really simple, but we could improve the technique of recovering velocity. In this case, this is the velocity, it's a cut of the aorta. This is a real patient, this is a cut of the aorta, and the idea is to recover the speed of fluid in a cut of the aorta, okay, from magnetic resonance. And to have a clean image with, okay, no aliasing. And this is the application. The main application is when you have a coarctation in the aorta, okay? This is a simulation we did with a student and a colleague. So you have a coarctation, so you have a high pressure gradient before and after the coarctation, and the idea is to estimate this. 2 minutes. To estimate this pressure without an intervention. The typical medical intervention is to put a catheter, and it's complicated. So this is typical MRI. These are MRI measurements of velocity. So you have essentially the Navier-Stokes equations with velocity measurements, and the idea is to recover the pressure. This is simply that, okay? So we propose some variational methods using, okay, test functions satisfying the Stokes equation, etc. But this is a typical application. So it's very important to obtain this without error, without aliasing, without noise, etc. And finally, two applications. We are working in porous media with homogenization, and also we have some results about recovering the air fraction in lungs, which is important. And also in elastography, we have this, I will skip that. We have these viscoelastic models in order to study the recovery of the viscoelastic parameters mu and lambda inside a viscoelastic model. Here is more theoretical. The idea is to prove stability and uniqueness using Kahneman inequalities for this type of problem, but this is another subject. So thank you very much.
Thank you for these interesting talks with a lot of